Hi all, welcome to tutorial week 4, COMP9417. Today we'll be talking about a few things, Bayes' theorem, discriminative versus a generative algorithm. We'll be talking about classification using Bayes' theorem, uh, naive Bayes, as well as a bit about logistic regression. So as usual, I'll go through an overview of the content. Then I'll go through the the tutorial questions, and then the Jupyter notebook. So let's get started. So yeah, as I say, it's classification. So just remember, classification is when your target is categorical. So for example, let's say you're predicting the species of fish, salmon or sea bass, or let's say we're looking at the Titanic data set and predicting whether people would have survived or not survived. So that's another example of classification. Say in insurance, whether you make a claim or not a claim, that's an example of classification. So these are when there's a discrete number of levels, right? There's a finite number of categories. Often it's not too many. Now you can have binary classification. That's when it's just one or the other, alive, dead, yes, no. Or you can have multinomial or more than two levels or more than two categories in your classification problem. So without further ado, let's jump into Bayes' theorem. So this is quite important. I suggest you get quite familiar with this. You don't need to know the proof behind this theorem, but at least know how to apply this. And I'm not sure whether you'll be given this formula in exam or not, but it's not too hard to remember. So a common example is in the case of cancer diagnosis. Now, this is a good example, but it also happens to form part of our tutorial question. So I'm just going to hold off going into this into too much detail until we go into our tutorial questions. But the thing to keep in mind with Bayes' theorem and why it's so powerful is effectively it allows you to swap around these two, right? It allows you to swap around, if you have probability of A given B, allows you to turn it into an expression where it's the probability of B given A. And this can be powerful. And in the context of classification, right? The thing that we are often concerned with is a probability of Y, say the target, given the features, right? Given the features, So of course, this could be something like we might care about what is the probability of, let's say the class being 1, given the features, the feature vector is equal to, I don't know, 1, 2, 3, let's say 0.25, etc., etc. So this is what our typical classification problem looks like, right? And in the context of Bayes' theorem and why this is relevant is there are certain algorithms that don't model the probability of Y given X, but they actually use Bayes' theorem to look at the probability of your features given the class. So they prefer to look at it that way, and they use Bayes' theorem in order to do that. But maybe I'm jumping ahead of myself. Let me just give you a simpler example first, just sort of make it a bit more concrete. But just keep this in the back of your mind that Bayes' theorem allows you to swap the A and the B. The probability of A given B can then be expressed as the probability of B given A. It's a nice little trick to swap things around, and this is used in a variety of different classifiers. Naive Bayes, one that we'll see in a bit. You can have some basic Bayes classifier, and the linear discriminant analysis, which I'm not sure whether it's in this course or not, but it also uses Bayes' theorem in its underpinnings as well. So let's have a simple example here. So this is just a basic use of a Bayes' theorem in order to perform a bit of classification. So I touched on this before, But this is Bayes' theorem, and within the context of classification, this is how we want to apply it. So, you can just memorize this formula and then just, you're really just, A in this case is the target, and B is the feature vector, right? And for this specific example here, Y, could be, say, your salmon or your sea bass. I'll just say bass here, right? And your feature vector, well, I mean, that's just these guys, and the features are, these are the features, right? So you are effectively using Bayes' theorem to swap around. This is the original classification problem, I would say. This is like your end goal. This is what you really care about, right? This is your classification problem. And I hope you understand why this is what we care about, why it's our classification problem. What we effectively care about is the probability of it being, say, salmon, given the features, or the probability of it being, say, bass, given the features. So I hope you understand that this is what we eventually care about. But we're using some trick here, I guess a mathematical trick in a ways. We use Bayes in order to express it in a different way, to calculate this, right? So let's see how it applies here, right? So let's say we want to work out what the probability of say it being salmon is, right? So that's the first example here. But you've seen a feature, and maybe this shouldn't really be a feature vector, because this one actually is just one feature, isn't it? So there's only sort of x1 here, only one feature, right? So this is the probability of y given some sort of feature, right? Now we start with salmon, right? And let's sort of see how this formula plays out here. So we use our Bayes theorem, and then we actually now want the probability of x given y. Now, and I repeat myself that this arrow here, it means vector, right? Vector. So there's multiple things here, right? It's not a scalar, right? You might also see it expressed like this, but they are equivalent, right? You might also see it, I suppose, it's hard to do bold, but imagine bold face, right? Anyways, so we'll flip it around. So we look at the formula. Okay. So what do we need? We need the probability of x given y, okay, and then we need the probability of y. Now, of course, in the first case here, right, y is equal to salmon, right, and then x, that's equal to 70, right? 70 centimeters, okay? And we just plug it into the formula, and when I say plug in, there's a small detail here, right? So what is the probability of x being 70 given it's salmon? So we don't actually know the true probability. So actually this is an estimate, isn't it? It's we estimate it by looking at the data and seeing historically or empirically what has happened. So we say to ourselves, okay, given it's salmon, that means we only care about here. Given it's salmon, what is the probability of it of the x being of the length being 70 centimeters? And we have our table here. That's this, isn't it? So this is a 0.4. Okay, so this 0.4 will flow into here. Okay, and then the next step is we want to work out what the probability of salmon is. Now this is actually given to us earlier, so maybe I should have just pretended I wrote something down here. Let's just say it's known. Now this is actually what's called a prior. It's called prior because prior to seeing any features, prior to actually seeing how long the fish is, this is what the probability of it being salmon is. But then of course after you see like let's say how long it is, then you change your view, right? So this is called the prior. And of course you could also have the prior for bass, which is 0.7 in this case. But this is given to us, right? And the prior can be updated over time. So that's the beauty of Bayes. It's you feed in your prior knowledge, and then over time this could perhaps shift. But when you apply this, just keep in mind that when we say the probability, we're using I guess the empirical frequencies as an estimator for the probability. So we use a empirical frequency as the estimate of the probability. Okay, because we don't actually know what the true probability is unless we've like seen every single like salmon and sea bass in the world. Likely it's some sample, but it's an estimate. That's a small detail, it's a small nuance, but it's something to keep in mind that we use the empirical frequency, and these empirical frequencies say unless somehow you've the population, you've tested out all salmon and sea bass, but these are estimates, right? Okay, so you plug it in. So I hope you understand now where the 0.4 and 0.3 came from. Now you might be asking, hold on, wait a minute, that's all well and good, but where is the denominator? Where is this p of x? Now this is why this symbol is here. This means proportional to, because this, it does not change. This denominator here, the probability of seeing the features, notice how like there's no y in there. Now what this means is that for both these expressions it's the same, right? So if you actually want the probability of the probability of salmon given you divide it by the same thing. Let me type it up because I suspect this might not be entirely crystal clear. So what I mean is the probability, the top one, you want the probability of y equals salmon given x equals say 70 cm, but what it actually is and you're going to divide it, you will get the probability of 70 centimeters given salmon times the probability of salmon. Okay, and then to that you divide it by the probability of 70 centimeters. Now on the flip side, if we want to work out the probability of the other class, in this case a sea bass, then we'll do the same, but I'm just going to change the target. But notice how this doesn't change in both examples, right? This guy and this guy, they don't change in either of those examples. So as a bit of a shortcut, if you don't actually care about the real probability, you can just sort of ignore this, which is what they've done here, which is why they're saying it's proportional, right? So another way of doing this is, you could do that, but then actually what is this is, do I have the symbol for what is the symbol for proportional? There it is. What is it called? Prop 2. Okay, yeah. So another way of looking at it is you could see it. You could see it like this, right? Oh, and if I get rid of this, so that's what that proportional symbol is doing there. Sorry. Let's get rid of these brackets. Okay. Yeah. So, but like, if you do want a true probability, you'd have to scale it by this p of x, probability of x, sorry, at the bottom in the denominator. Otherwise, you may have noticed actually that this does not sum to 1, which disobeys the law of total probability. But that's okay because these aren't probabilities because it's just proportional to it, right? But if you scaled it and made a probability, yeah, you'd have to add up to 1. Otherwise, you've done something wrong. It's got to obey the law of total probability. Okay, so cool. So like in practice, what you do is if you're given a data set like this and you're just using a basic Bayes classifier, you would calculate the probability of all the classes, and then basically what you do is your target, your predicted value, you just take the maximum of these two. Oops. You take the maximum of both your of this 0.12 and the 0.35, and in this case you can see that the maximum is CBAS. So given the data you've seen, you predict CBAS because it's more likely, which makes sense, right? I mean, you generally want to predict something which is more likely based on your model. Okay, so that's the basic Bayes classifier. I stress it. It's important to understand this example. It's also important to understand Bayes' theorem, because all this stuff will later today is going to build on this. So if you're watching, maybe pause and have a rewatch, because yeah, everything's going to build on this. So if this isn't entirely sticking, it's going to only get worse when we look at naive Bayes. Okay. The next thing I want to talk about is what's called a discriminative versus a generative algorithm. Now, the nuts and bolts of it are that the discriminative algorithm, you can think of it as just you model what you care about directly. So the probability of y, the probability of a target given the features, that's generally what you care about, and your model will explicitly take care of that. So and then on the generative side, this is when you use Bayes' theorem to flip around, that probability of y given x, right? And you calculate the probability of x given y, right? So one way to think about it is it's discriminative. It's a discriminative algorithm in general, unless you have to use Bayes' theory to do some fancy stuff and swap things around. So you can see here, going from here to here, that's using Bayes' theorem, right? So with the discriminative algorithm, you go head on, and you just model the probability of your target given your features. So many models are like this. So some examples are your logistic regression, your support vector machine, your decision trees, your k-nearest neighbors. Now, your generative, you basically you flipped it around, haven't you? So instead of modeling the probability of your target given your features, you flip it around and you look at the probability of your features given your target with some stuff at the end, right? Now, why is it called generative? Because you've created a distribution. You have a distribution, a probability distribution of x given y, right? Now, this basically means that for a given class, let's say for example, we have two features. Oh, actually, yeah. Let's say for example we have two features, and we're doing the whole CBAS example, and let's say this is maybe this is a length. Sorry, that's some terrible writing, isn't it? So let's say it's length, and let's say this is width. Okay. Now, if you've done your generative model, you have some distribution. You have a model of the probability distribution of your features, which is this given y, right? So it might look something like this. So let's say in this case, y, we're looking at distribution of the distribution of these features given y is equal to, let's say, just say CBAS. Let's make it up based on the length and width of the fish. I'm going to draw a heat map here. So it may look something like this, depending on how you've done it. So this is a contour sort of plot. So what this is saying is that given its CBAS, like the probability, this is the probability. The probability is super high here, right? So if you have a fish, if you have some sort of fish which is of this length and this height, it could have that could have, say, like a I don't know, like maybe it's a 0 point, maybe that's 0.9% chance according to this model of it being sea bass. And then maybe you have like some other point here. You put in another guy here, another data point, and it's far less likely. Maybe this one only has a 0.05% chance. Sorry, 0.05% chance of being sea bass. So this is the contour plot here. So I'm trying to give you a bit of a flavor as to why it's called generative, because it allows you to generate the distribution, this sort of distribution. It allows you to generate the distribution of your features given your class, and this is something you can't. It's not easy. Not as easy to do with a discriminative algorithm. Okay, so hopefully it gives you a bit of flavor. Now, I hope we're all comfortable with Bayes right now, or a bit more comfortable. Let's move on to the naive Bayes classifier and why it's so interesting. So, as the name suggests, the naive Bayes classifier uses Bayes' theorem. As you can see here, here's Bayes' theorem, right? But there's an interesting thing that it does, an interesting step it does. It's called the naive Bayes assumption, which it uses to simplify things a lot, right? So, generally with your Bayes classifier look like this, and then we use Bayes' theorem to flip it around, and then basically we try and maximize the probability. So we want to find like you can create this expression for multiple targets. Say y is equal to sea bass, y is equal to salmon, and you want to find out what is the most probable. So expressed mathematically, what we are saying is, so we want to test out, I guess, test all the classes. We want to test all the classes out, right? We might try, say, you might try, say, v is equal to, say, salmon, or say v is equal to sea bass, right? And then you calculate the probability, and then your y hat, this is your y hat, your predicted value will be equal to that, right? Now this is the original expression. This is y, and this is the feature vector. So that's this guy. Now then we use Bayes. We come down here. We use Bayes' theorem to flip around x and y. So now we have x here, and then we have y here, and then that's y again. And what we want to do is just take the maximum, and you can see here, right? So maybe I guess argmax is the same, but I guess these two are proportional to each other, right? So going from here to here, it's proportional, which is why the argmax is the same, because you just have this factor here, which is a proportionality constant, and you go from here to here, it's the same argmax, it's the same maximum. Cool. So that's just Bayes again. Now let's see what this naive Bayes business is all about, what the difference is. Now, there's something called the naive Bayes assumption, and it allows us to simplify the probability a lot. So this is the original probability we're trying to maximize, right? We have this expression here, the probability of all your features, given your target, right? That's this here, okay? But the problem is this is not an easy thing to sort of unravel, right? If you expand it out, effectively you have to go, the probability of the first feature given everything else times the probability of the second feature given everything else. And why is this? It's that the features given the target may not be independent, right? So I guess you could say, because the problem is given say y, xi and xj may not be independent, which is why you have this long expression here. Which is why you have this long expression here. If you want to break up this joint probability, right, into separate conditional ones, it'll look like this, which is an ugly expression. It's not nice. So this is when we use our naive Bayes assumption, and I'll unpack why it's called naive in a bit. The naive Bayes assumption basically says, given given a target, these guys are all independent, right? Which means if they're independent, to get the joint distribution, you just multiply it all out. It's all good. And this is much easier than this. So it goes from here to here using the naive Bayes assumption. And it makes things a lot simpler. A lot simpler. You don't have to consider given everything else. It is much simpler dealing with this. So what's what I'm saying? So the attributes or the features are independent given the class value. So remember, this is what we're trying to do. We're trying to argmax the probability of your features given your class, right? But to simplify this expression, we use naive Bayes, which allows us to express it like this. It's much easier. Now, the reason it's called naive is because often, this isn't the case, but also often it's good enough. It might, even though it's not perfect, often, despite this assumption not really holding, often it is good enough, and often the model does fine anyways, right? Yeah, and just trying to think of a bit more of a concrete example. Yeah. So let's say, for example, we're trying to predict whether someone's obese or not. It's whether someone has heart problems, cardiovascular disease, and all right. So in that case, let's say the target is like cardiovascular disease or not. Or not. So let's just call it 0, 1. So 1 is cardiovascular disease. Now, let's say that one of the features you care about is the probability of, let's say, high blood pressure. Let's say one of the features is high blood pressure. High blood pressure, given, let's say they have cardiovascular disease. So let's say X1 is high blood pressure. Let's say the second feature is what correlates with that? Let's say diabetes. High blood pressure. Maybe hypertension, or maybe that's the same thing. Sorry, I'm just trying to. Again, I'm not a doctor. I'm just making stuff up here. Let's say I don't know, some sort of cholesterol levels. I'm working here with the assumption that these two are correlated in some way. I'm under the impression they are, but I don't know. So if we look at this, and we look at this, let's say high cholesterol, right? Cholesterol. That's how you spell it. Yeah. So, in theory, we should have like, if we want the full expression, we want the probability of high blood pressure, given everything else, times the probability of, like, say, high cholesterol, given everything else. Now, you can probably see the problem here, right? These two are probably quite correlated. So, like, the probability of high blood pressure, given high cholesterol and CVD, is probably not going to be the same. It's not going to be the same as probability of as this, right? And this effectively is the naive Bayes assumption. The naive Bayes assumption just says that, given the target, given cardiovascular disease, your target, so your feature is independent of all the other guys. So this is one example here. So the naive Bayes assumption says this is good, no problems. But we know that this is probably not the case. The probability of someone having high blood pressure, given they have high cholesterol and CV, is probably higher, right? Than it's, if anything, I would argue that it's probably something like this. Again, I'm a doctor, I'm just guessing, right? So that's just a bit of an example as to the problem with the naive Bayes assumption, okay? But as I say, in practice, often it's okay anyways. Now, let's dig into an example. Let's dig into an example using naive Bayes, right? So here, what do we have here? So in this toy example here, what we care about is so what this is it's whether we want to play tennis or not. This is an example from one of the lecture slides. It's whether you want to play tennis or not. So whether the conditions are good to play tennis or not, given some features, Say for example, if it's not too sunny, it's good temperature, humidity is okay, not too windy, yeah, let's play tennis, But then if it's raining and it's cold, it's windy, let's not play tennis. It's no good. It's a silly example, I know, and it came from the slides, and I think it also before that came from some website. I forget the name, but I grabbed it from the slides. It originally came from some websites. I think it was analytics video or something, but I can't take credit for this. Is what I'm saying. It came from the slides, which grabbed it from somewhere else. Anyways, so in this example, what we are interested in doing is applying the naive Bayes classifier, which is this guy here, right? We basically want to test out, and this is the V here. We want to test out, yes and no, and we want to take whatever is maximized, right? So what we want to do is we go, okay, what's the probability of play tennis? So in this case, it's 3, 4, 5, 6, 7, 8, 9 divided by 2, 4, 6, 8, 10, 12, 14, 9 and 14. Say there'll be 9 and 14, and you fill the rest. I'll go to the next slide because I think it makes it a bit more concrete. But effectively, what you do is you apply this formula, right? But then you use the empirical frequencies to plug everything in. So what you do is we start off with yes. So I would say V is equal to yes in this case. So that is this guy here. So let me just draw a line. Okay. And then we want to multiply all the features together here, right? So, but how do we get the probability of yes? We just use, this is called the prior, because prior to seeing any of the features, what's a chance of playing tennis? And what it is you look at the number of yeses, 1, 2, 3. There's 9 of them over 14, and we use the empirical probability. So this one here, that will feed into here. Okay. Then we'll go through the rest of our formula. You go through each of the features, and then put in the empirical probability. So feature 1, let's say sun. Now, what's the probability of it being sunny? Given it's a yes, we play tennis. So out of all the examples where it was sunny, so sunny, 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 sunny. Oh, sorry, it's all of these, isn't it? Sorry, it's not sunny. It's sun. So out of all the sun, so what we want is given we play tennis, which is this one, this one, this one. So it's these 3. This one. Okay, so it should be 9, 2, 4, 5, 6, 7. Okay, given we play yes, plays yes, we want to work out what the probability of it being sunny is, right? Yeah. Equal to class. So what we then do is we look into here and we count the number of times it's been sunny, which is here and here. So that's 2 out of your 9, which is where we get this guy here. Okay. Now we repeat this exercise for the rest of them. So we look at if it's cool or not. We'll look at if the humidity is high or not, and if it's windy or not. Right? You repeat the same exercise, right? So if it's say cool or not, again it's so these guys here. So how many times is it cool? So that's 1, 2, 3. Yeah. So it's to 3 out of 9. So that's here. And that's this guy here, the 3 out of 9. So that goes into here. And then you repeat that exercise. You multiply it out, and then you have a look, and calculate the probability. So I should have mentioned. Sorry, we have a new instance. This is our test data set here. We could say, right? This is our test data set, and then we apply naive Bayes by having the prior, and multiply it by the probability of seeing that feature, which is sunny here, given the prior, given it's yes. Then we do the same thing for cool. I apologize for the lines everywhere. It's going to look a little messy. Okay, so we do that, and then we repeat this exercise using no. Well, we do the other side, okay? And then you can see here that looking at these two, this is greater than 0.0053. So in this case, our y hat, our predicted value here is no. We don't want to play tennis based on this. Now, if you want, you can normalize it, and you can have it so that if you add it up, it equals to 1, obeying the law of total probability. But you don't need to for the prediction. If you want the probability, yeah, go ahead, scale it by the normalization constant. Cool. Now, the next nuance about naive Bayes is you may have noticed here that these are all discrete. These are all discrete features. It's either sunny or categorical. These are categorical discrete features, only like a limited, finite number of levels. That may raise a question, right? Hold on. What happens? What happens if one of the features is real? What would happen if let's say I had another feature. Let's call it x5, and it was say I don't know, pressure, like atmospheric pressure measured in bars. Is it bars or atmospheres? What's the SI unit for pressure? Pascals. Yeah. Okay. So let's call it kilopascals. Again, I don't know anything about what is the pascals normal air pressure? Let's have a look. Pascals kPa. So 100. Let's go 100. Okay. And so there's apparently 100 kPa is normal. So let's just, maybe our features might look like this: 100, 150. Again, I'm making this up. I don't know what normal is really. So on and so forth. So you might have another feature which looks like this. And it could be that each of these values only occurs once, right? And if you plot it out, kPa, it might look something like this. You might have a point here. Sorry. You might have a point here. Say there's 100, 100, 125, 100. You know, it might look something like this. Now, in reality, maybe it's a normal distribution behind it, but because your data points, you know, it's so granular. Maybe there's 100.125 or something. You know, 0.1, 0.5. You know, you might only ever see each value once, right? But that it's gonna like mess things up because each of these will appear once. You're not really getting a proper view because you're applying a discrete sort of empirical frequency estimates to what is inherently continuous. So I've hinted at the solution here. The solution as you maybe let's just fit a normal distribution to it, because maybe the data actually looks more like this. Sorry. Maybe the data actually looks more like this. So I'm trying to like clump that. So there's some clumps in the middle. So there's more data points in the middle and then it sort of tapers off here. But there's more clumps in the middle, and it's normally distributed. So that's one way around it. You can assume that the features are normally distributed given the class. Cool. Now another extension of our naive Bayes here is we can extend it using what's called a multinomial or Bernoulli naive Bayes. Now it is still naive Bayes because you assume independence between all the features, right? Now, but what distinguishes multinomial and your Bernoulli naive Bayes is you make an assumption as to the distribution of x here, right? You assume it's multinomially distributed, or you assume it's perhaps multivariately. You assume it's Bernoulli distributed, which is where this guy and this guy comes into play, because effectively you're replacing this guy here with either this guy here, or you replace it with this guy here. And the reason why you can do is you make more assumptions. If you assume that like all the features with respect to the target are multinomially distributed, you could look at this. If you make the assumption that they're Bernoulli distributed, you could look at this. Now, just for a bit of flavor, this is an extension on your binomial distribution. So it's a generalization of your coin toss. So this is, let's say, number of heads in, say, n coin tosses. Okay? You can think of it as, say, number... You can even apply it to, say, die rolls, because now you have die rolls would be multinomially distributed. Okay, yeah. So yeah, die rolls here will be multinomially distributed. Okay. Yeah. So we'll go through this in a bit more flavor when we get to the tutorial questions, which I should probably get to quite soon. Last thing I want to talk about before I move on to the tutorial questions is logistic regression. You may recall regression. In regression land, effectively what you're trying to do is you are fitting a line of best fit. So you'd effectively have something like this. You'd have a feature, so x1, and then you have some sort of response or target, say y. You'd have your data points. Sorry. You'd have your data points like this, and then you fit your line of best fit, which may look something like this. Okay? Now, the thing to note about your linear regression is that your target could, in theory, take any real value. This doesn't really, unless, of course, I mean, there is a degenerate case where your model just has the intercept term, but but even so, you have the epsilon. So sorry, this remains. The target in theory could take any real value. You know, of course, the more extreme it is, because it relies on the error term. You know, if you have an intercept term, the error term will be driving things up and down to plus and minus infinity. But of course, it will, you know, the further away from the mean or zero, the lower the probability. But yeah, this in theory could be, you know, plus or minus up to plus or minus infinity, right? You may notice but let's say we want to go from regression land to classification land. Now, or better yet, we want there's a probability. We want to go to classification, and we want a probability of it, say, being, you know, class 1 or class 0. Now, what we need to do is we need some way to go from the real values, and we need to go to here between 0 and 1, because that's what a probability has to be. A probability has to lie between 0 and 1. We need some way to squish this function here into 0, 1. Now enter the sigmoid function here, right? This is the sigmoid function. It takes in any real value, you know, so it could be, you could even enter in, say, like, let's say plus, I don't know, let's call it 10 million, and it might spit out like, and then you put in the sigmoid function, it might spit out like 0.99, just like a lot of nines, right? It's asymptotically close to 1, right? Actually, I don't even know if it ever touches. Let me check out the domain, because it might just asymptotically, it might be an asymptote rather than ever touching it. Where is, sorry, the range? Is it 0 to 1 inclusive? Because I feel like it might be exclusive. I don't know if it'll ever touch. Actually, it's probably being a bit too pedantic, because I guess when it approaches infinity. Anyways, I'm just being pedantic. I don't know. I don't think it actually matters too much for our sake whether it's one of these, like whether it never touches, like it asymptotically approaches but never touches, or it's one of these. Either way, I'm just gonna leave it like this. I think it's fine for our purposes. So what we're doing with logistic regression is effectively, and let's say like over here it reaches like, let's say 100, and down here it reaches, say, -15. Now what you do here then is you will transform it. You will apply your sigmoid function, and then it will look something like this. You're applying the sigmoid function to your linear regression here, transforms it from a range of -15 to 100 to 0 to 1. Fantastic. That's exactly what we want, right, for probability. So I think that's to me, that's the easiest way to think about logistic regression. You're doing the same, you're doing the same thing as linear regression, but then you're applying this like sigmoid squishification function to get it to between 0 and 1. Cool. Let's talk about our tutorial questions. Question 1. Let's consider the Bayes theorem to apply to that cancer example on slides 22 to 26 of the lectures. Great. This is our Bayes theorem, and this is our question here. Now, I think there's a couple of ways to think about it. We can just apply it blindly. It's not the end of the world. Maybe I can just apply it blindly, and I'll give you a bit of intuition as to how to go about doing it. But remember the Bayes theorem. Actually, I'll use this notation here. But in this case, so H given E. And then in this case, we have, what we care about is we want probability of cancer, and then let's say E is equal to positive test, because that's what we care about. Because in this example here, we've got some numbers, all right? Probability of cancer, this is positive as in positive test. And what we actually care about is we want to work out what the probability of effectively cancer given a positive test is. That's what we care about. We're given a bit of data, about like the prior. These are the prior. These are the priors. We're given a bit of information on the priors, and we're going to be given a bit of information as to the sensitivity and specificity, or in some ways the accuracy of the tests. So here, the probability of, so this would be the sensitivity, the probability of them having the disease and picking it up as positive. And this is, I guess, so here this would be a true positive, because they're positive for cancer and it's true. This would be a false negative, because, well, it's come up as negative, but it's false. So this is a true positive rate, false negative rate. This is, what is this? Positive, but it's fake. So this is false positive rate, and this, what is it? This must be a true negative rate. Okay. Given all this, this is our task. Our task is to work out what is the probability of the cancer given a positive test. So what do? We apply a Bayes theorem. So we want the probability of positive given cancer, and we're just applying this formula. So remember, H here is your cancer, E here is your positive. So H, E, H. So H. Hold on, have I done this right? Oh yeah, no, sorry. Yeah. E, H, and then cancer. Okay. And then we want to divide this by the probability of it being positive. I'm just going to change notation here. So I'm butchering the notation a little bit, just bear with me. Cool. So we apply Bayes theorem, okay, and then we get something like this. Okay. Now, what we do is we just plug it in order to get the result. So, what is the probability of positive given cancer? It's 0.98. Now, the prior for cancer is 0.08. And then we want to multiply it. So, divide it by the probability of it being positive. Which, okay, so that this requires one extra step, the probability positive. So the probability of receiving a positive test basically will, let's go first principles. How do you get a positive test? Either you have cancer and it comes back positive, or you don't have cancer and also comes back as positive. Okay. So in this case, what's that equal to? I'll do it down here. Positive given cancer, 0.98. I think it's this again. Okay. Then, what's the probability of positive given not cancer? That's 0.03. What's the probability of the prior of no cancer? 0.992. Now, just go to cheat a bit. I don't want to use a calculator. Feels like I made a mistake. I can't remember what the answer should be. It's the first one, isn't it? Pretty sure it's the right one, isn't it? Let me just check it by looking at the top, and I'll see if I get the scaling factor right. I just want the top bit, don't I? Yeah, 784, which I think is, yeah, 784. Sorry, I missed a decimal place, didn't I? It's meant to be 00. I made the exact same mistake last week when I was talking to a student about it. There we go. So, the probability of cancer given a positive test is just this. About 21% or so. Of course, in the example here, they didn't bother scaling it. So if you just look at the top, this is why this doesn't sum up to 100%. But you could repeat this exercise. For the probability of it being not cancer given a positive test, or you can just 1 minus. It's really the same thing. So like say 89% say for the other side. Now, this may be a surprising result, and I just want to give a bit of intuition as to perhaps why this might be the case. How much time do I have? Intuition. Do I want to give the intuition? Because it takes a bit of time. I'll do it quickly. It takes a bit of time to draw up, but I'll do it. Now, this might be a surprising result. Because that's odd. If I get a cancer result as positive, why I don't have cancer? Really, that sounds too good to be true. What's going on here? Let's pick this apart. Excuse me. Let's say this is our world of people that get tests. Let's say this is our world of people that get tests. All right. Let's not fill it in with anything. It's bigger. Okay. Now, let's subdivide this into the people who have cancer. So what is it? It's like less than 1%. Let's just call it like this much, right? So these are all the people that have cancer, and I'm just gonna make this red because cancer's bad, and then the rest of everyone else is here and they don't have cancer, which is good, so I'm gonna make that green. So not cancer, cancer, right? Now, out of all the people that have don't have cancer, the chance of it coming as positive is 3%. So what does that say? Again, this is not to scale, but I hope you kind of get the idea. So let's say positive test is this. Let's say purple means positive test. Actually, maybe I'll do no outline and yeah, okay. So let's say then these are all the people that came back with a positive test. Right? Just try to make it easy to see. Okay, cool. So these are the people that came back with a positive test. Now, let's work out the same bit for the people that actually have cancer. So let's say you actually have cancer. What is the chance of it coming back positive? 98%. So that means we want 98% of this guy here. Let's call it this much. I hope this is making a bit of sense here, because I'm trying to show you how, like, if you look at the entire population, what's that color I use? So these are positive. These are people. These are positive tests, right? But these people have no cancer. These are also positive tests. The other sliver here, so this little guy here, right? These people actually have cancer. Now, I hope you can imagine, if you look at the ratio, of those two, so say if I get, what I care about is the probability of, say, cancer given positive is going to be equal to this fat rectangle here divided by this small rectangle here, right? So you effectively have like this big chunky guy here, right? Sorry, other way around, isn't it? I should redraw those arrows. So that, like, so these purple, these are all the people with positive tests, but out of all of them, right? It's really something like this. You have like this tiny sliver here, right? This little tiny sliver here. You know, these are the people who have cancer and it's positive, and then, oh man, and then it's swamped. It's swamped by the people that don't have cancer, right? But still come back positive. It's just purely because there's like the incidence of cancer in this example is so low that even if you pick up all the positive, it's just dwarfed by the false. And bear in mind, these are false positive. It's dwarfed by the false positive that are just coming through. So that's a bit of intuition as to why this is the case. Now the actual tutorial question, that's the first part. Now it says consider the example. Now what happens if you order a second laboratory test and the test comes back as positive again? What are the probabilities of cancer and not cancer? Now, the extra step here is you do a second test, right? So, what is happening? What is going on? Now, these are the exact same numbers from before, right? Now, this is basically what we talked about before. This is what's in the lectures, right? After one test, and you should be familiar with this. That you know, this example here is this guy here. Okay, so we should agree now that the maximum a posteriori. Gosh, I never say that word right, is it? I think it's a posteriori. Maximum a posteriori. A posteriori. Look, I'm just gonna say a posteriori. MAP. I'm just gonna say MAP. I'm definitely not pronouncing this right. I apologize. The maximum a posteriori hypothesis. So that's what I'm trying to say, but I'm not actually saying it properly. But this MAP, the maximum, the more likely, given what we've seen, outcome is that it's not cancer. But the question is, what happens if we do a second test, right? Now, what we can actually do is we can repeat this guy, right? So this is the first. I think we've been through. That's fine. We've been through the maths here. Now, if there's a second test, effectively, it's another one. So this is the first test. And this is the second test. Now, the key assumption here is that with the tutorial question is that we assume that the two tests are independent, which is why we can multiply these two together, because we assume independence, right? So the chance of seeing two, so these are the two hypotheses, right? So this is, the top one's cancer, the second one is not cancer. That symbol at the beginning is not cancer, right? Now, the probability of, you know, the second test coming positive. So this is the what the question's asking, right? It's saying, now assume, so let's say you have two. So this is asking about two. What happens if you have two positive tests, right? So first positive test, given it's cancer, times second positive test, given it's cancer, times the prior, right? And you do the same for both, right? You test it out for cancer, not cancer, and then you want to take the MAP. Now, in this case, given you've had two tests, actually, now we say it's cancer, right? Which is kind of interesting, right? But after having one test, it is, you know, it's more likely, significantly more likely to be not cancer. But now you take a bunch that are both positive. It's just the more tests you take, the more likely it is going to be cancer. There's a note here. Notice how quickly the probabilities get very small. Now, if you add another one of these, it's just going to, you know, decline in a log space. And you can see what's happening is, you know, so you can see what's happening is the first one is going 0.98, 0.98, 0.98. The second one's going 0.3, 0.03, 0.03. Let's actually plot it. Let's pull up our good friend Excel. Our good friend Excel. What do we have here? So let's say this is number of tests, number of positive tests, not sorry, number of positive tests. Let's just do that. And what do we have? So we have and then what this is a probability of, you know, say cancer, given you know, all those positive tests. And then probably not cancer, given all those positive tests. Now, what would it look like? It is this. 0.98 power of this guy here times 0.08. Oops, that's an extra zero there. You may recognize this number because 0.98 to the, oh, it's two of them, isn't it? That's why, if I go down here, 784. Hold on a tick. Oh, that's 0, isn't it? I should start at 1. Sorry, there we go. That makes more sense. Now, same thing here, but what we have is 0.03, so 3%, and then it's 992. Cool. Now let us do the fun stuff. Plotting. What's a good plot? So, oops, that was a bad move. That's a good way to show it. Yeah, I mean, yeah, sure, why not? They both add up to 100% either way, I guess. Oh, actually, well, they're not scaled, so maybe they don't, but this scales it up to 100%. Yeah. So there's a few different ways you can view it. So you can see here, right? Like, I mean, it's kind of hard to see the declining into log space or whatever, right? Is this right? Oh, let me scale it actually. Yeah. Might make more intuitive sense if I scale it to something out of 1, because I'm just looking at like, well, it's kind of hard to see the logarithmicness. Actually, sorry, I just haven't done this right. Probably of cancer, given all those tests, that's this one, isn't it? So 0.98. Oh, that's the problem. The problem is a scaling factor. Yeah. That's why it's declining. Yeah. Okay, so maybe this graph makes more intuitive sense. So it's a little hard to see here because it gets really small really quickly, but after one test, you know, the chance of you having cancer is only like 21%. After 2 tests, the chance of you having cancer is like what, 89%. 3 tests, the chance of you having cancer. Wait, is this labeling right? No, it's that one, is it? Yeah. So yes, after 1 test, it's 21%. 2 tests, you know, the chance of you having cancer is like almost 90%. Ignore the label because this one is unscaled. It's a relative risk. After a few, it's 99, it gets high. It's just exponentially. Oh, I don't use exponentially, but it is rapidly shooting up towards 100% with every single positive test. It just confirms it, which you might say that it's an obvious result. I mean, if you got one cancer test, you might not give much faith, but like after you take 3 cancer tests all positive, you probably give a lot of faith. But anyways, that's just a bit of flavor as to what's happening here. I should probably speed up. Cool. Yeah. The next question here, this one's a little more involved. Let me just pull up my face. Here I am. Hello. So, document classification. Now, Omar Gaddis has this great Bayes supplement, which I highly recommend. I think he will upload it. But it goes through it in some detail. It's quite nice. It's this little PDF document here, which I recommend. Highly recommend. I've just pulled bits of it into these slides just to talk about. But let's just have a think. What are we trying to do? It's document classification, and we're trying to basically work out, is a document, spam or not spam, based on the words that appear in it, right? So spam or not spam. Right? And our data set looks like, say, this. So these are like documents, right? We have like 8 like documents or 8 emails or whatever you want to think about it, right? And these are, I guess, words. These are the words, and this is obviously a simple example, but these are words in the document. And say B might be like, I don't know, like hello or something, and then D might be like offer. I'm making this up, but these are just words of some kind. Obviously, this is a simple example. Now, real life, this would be far more complicated. But just to keep it simple, we'll just assume there's only like 3 words, and each email has like 2, 4, 6, 7 words in an email. But again, it's a simple example. Just bear with me. This is the data. So it looks like. Now we simplify it by converting it into this form or this form. So this form just counts up the number of each word. So for example, for document 1, we have A appearing 0 times. We have the word B appearing 1, 2, 3 times, right? And then C appearing none. And in this case, we assume that what is it? D and E are what are called stop words. So this is a concept in natural language processing. So it could be just words like the, of, at, just words that, I mean, they do carry value, but in a simple example, they may not carry as much value as, say, offer or free or Viagra or I don't know, like what are some scammy words? Yeah, free, discount. The kind of stuff that appears in spam emails, right? But these are stop words. Maybe it's like the, or maybe it's of, which do carry value to say. But this is a very simple example. I mean, natural language processing gets far more complicated than this. But this is a simple example, so we just ignore the stop words for the time being. Okay, if we want to use what's called the multinomial version of this, we need this, but in the lectures I think they only covered the binomial, so that's this. So this just models whether the word occurs or not. So whether the word appears or not. It doesn't bother counting it, it's just whether it's there. So for example, let's say in the first example, the word hello appeared 3 times for the first email. Using this is the data set for your, I guess, Bernoulli. Sorry, no. Your Bernoulli, I think I'm spelling that wrong. Bernoulli? Yeah, your Bernoulli, Bernoulli naive Bayes, right? And you just model like this, just whether the word appears or not, like a binary, 1, 0. Why is this naive Bayes? Now, this is our naive Bayes formulation, and this is our target, and what we care about is, whether it's spam or not. Right? Yes or no, spam or not, right? And we have the probability of a feature is given the target. Now, with our Bernoulli assumption here, what we do is we basically express the probability of, there's a probability of seeing a word, like let's say seeing, say, hello at all, like do you see it or at all not, given, let's say it's spam, and we just model it as just like a simple, just sort of, is it there or not? Bernoulli distribution. Bernoulli distribution is just like, it's one of the simplest distributions around. It just doesn't happen or not. There's two outcomes. There's two outcomes, like 0, 1, and the probability is just one or the other. It's just a fancy way of saying just an experiment where two things can happen with probability p and 1 minus p, I suppose. So in this case, you model the probability of seeing hello, as just, say p, some sort of p. Let's say p hello, given that it's some sort of spam email. And then the probability of not seeing hello is just 1 minus that, right? Cool. So you apply this to everything. So in the first email instance, the chance of seeing that is, you go, say, the chance of it being spam would be, say you'd have your probability of, maybe I should type it up. You have, say, a probability of, a spam. And then you just, put in probability of the prior of spam times the probability of, let's say, no word A given spam, no word A given spam times the probability of no, word B given spam times the probability of, probability of word C given spam, and then of course you'd have your scaling factor, probability of seeing, the document E1, right? That's why it's naive Bayes. We're assuming independence between all these words. So the probability of it, given it's spam, the probability of seeing the word A, say hello, is independent of the probability of seeing, I don't know, let's say offer is, let's say it's A, right? Maybe A is offer. So whether or not you see the word offer, it's independent of whether or not you see the word hello. Okay. Yeah. So let's dig into the maths a little bit. That was a bit of a primer. Yeah. So here's our data. We model it like this. This is our naive Bayes assumption. Okay. You plug it into your formula. This we modeled using your Bernoulli distribution, which goes into there. If you're, again, this is a simple experiment. Two things can happen with probability p, 1 minus p. Google it. Bernoulli is very, very simple. Cool. Now, the question on your mind is, where do we get this from? Like, what is this? How do we estimate this? This probability of, what is it? What's K? Is K the word? No, K is a class. The probability of, say, like, some spam, given it's spam, the probability of seeing, say, word, I don't know, say A, right? Like, what is it? And how do we estimate it? Good question. The way we estimate it is empirical probabilities. So you just look at, like, for example, this is this could be, say, spam. So you look at all the documents that are spam, right? And then you look at the number of times that, say word, like it could be word, say, hello. Maybe it's word B, right? And then you look at the times the word J, right? So you look at all the documents of word J, and then you look at the proportion, right, that it happens. So basically, there's a probability that it's spam, and you see that word, right? So you look at all the spam emails, right, and look at the number the frequency that the word hello appears. You repeat this, and then you plug it into the formula. So here are estimates. So like positive here, remember positive here is spam. Let's try a bit of cursive, hey? Okay. So for example here, given it's positive, so these are positive, mind you. The red is positive. Given you're positive, what's the chance of seeing A? So let's have look-sees, you know, that's 1, 2, so that's 2 and 4. So if you look at, you know, to work that out, you look at here, you look at this, you look at this guy here. Then, you know, let's just look at another example. Let's say you're like, okay, given you're not spam, what's the chance of seeing C? Or you go here, and you're not spam, and you look here. 1 and 4, okay? Then you simply plug into the formula, right? Plug in the formula down here. You have your class prior. You test out both of them. You test out the class prior here. In this case, it's spam, right? And then you multiply out all the probabilities of seeing the feature, given it's spam, and you get a probability. So in this case, it's a 9. The probability of it's being spam, given the document, given the features, I'm just going to call it E, given the E that you saw, is equal to 964. So then you conclude your prediction, your maximum A posteriori would be that it is not spam. Of course, you can repeat this exercise for the other side, but you just get like what, 55 on 64. Okay, cool. Jupyter Notebook time. Now, this will be in the Google Drive. So I've shared the whole folder for the all my slides, and as I save it, it'll sync up to my Google Drive like that, and you should be able to see it shortly. The stuff I've written at the end. Okay, Jupyter Notebook. Where are we? Yeah. Okay. Yes. So what are we trying to do? There's something called the Titanic dataset. The Titanic dataset is, you know, that ship long time ago, was early 1900s or something, ran into an iceberg. Some people survived, some people didn't survive, and it's basically trying to predict based on the features. So, you know, whether they're male, female, what class, age, how much they pay for the ticket, etc., etc. A whole bunch of features there. Whether or not they passed away or not. Now, let me show you the data set actually, maybe give a bit more flavor. This is what the data looks like. Sorry, I've disappeared, haven't I? Okay. This is what the data set looks like. Yeah, so this is our target. And, Mac Excel. Come on. And these are our features, right? So I mean, this will probably be useful. Name, you know, like you could probably extract some things out of it, like Mr., Mrs., Doctor, Reverend, etc., etc. You could do some feature engineering. This, but we know, like, you know, from not subject matter expertise, but, you know, just know a bit of history. We know that sex, you know, the age, where they were, you know, what cabin, the lower deck, upper deck. You know, the class had a big impact to play as to whether or not they survived, and you could probably just, you know, you can cut it. Again, you should probably do this in your scikit-learn, but I'm being lazy. I'm just being lazy here, to be honest. Yeah. Some have survived. I want percentage. Yeah, so you can just do like simple one-way cuts, and you can see here that, you know, how does it? If it's looking at like 73% of females survive, 20% of males survive. This would form kind of like exploratory data analysis. You could cut it by other things. You know, you look at passenger class. I think the class 1, yeah, the richer you are, the higher chance of survival. You could probably also cut this by age, but you might want to ban them. Where's age? Here we go. Oops. There you go. Yeah, you might want to run a linear regression on this because this is a little hard to see, isn't it? Because there's too many levels. Now, where's my linear regression? Let's do it this way. Let's see if there's any link, right? So what's on the x-axis? Is this the right way to do it? No, it's not the right way to do it. If I'm trying to see if there's a link between age and actually no, it's already done here. What am I doing? Anyways, that's a view of the data set, right? And you know, given all this, there's a few things we can try. Now, there's a really basic model here which they initially suggest. Effectively, they're just cutting it by what are they cutting it by? Passenger class 1, 2, 3 and gender 0, 1. And you can see here, I think one's female, right? So you can see here that you know, whenever there's a 1, it tends to be, you know, a bit higher. The females had a higher chance of surviving. You know, women and children first. What they used to say back in the day for the lifeboats. But we also see that the better the passenger class, the higher chance of survival. Yeah, look at the males. Look, 14%, 70%, 39%, 45, 90. Yeah, so you can see. So there is a positive correlation between, well, a negative correlation between class, because number 1 is better than number 3 in terms of class, and also with gender, the females tend to survive more. Now, the question is, why can't we just use this approach? This sounds pretty easy, pretty simple. What are some problems? There are a few problems. One, this model is really simple. It's only looking at 2 factors. When you have a simple model, it might have a high bias. It might be too simple to capture all the nuances of the data. You might need more features. It's really simple. It might miss a lot of conflated variables. It could lead to inaccurate conclusions, right? Now, the problem with this approach is you could increase the number of features, right? But the combinations increases exponentially, right? Which means that the number, this is the curse of dimensionality, which means that the average number of data points per partition is going to increase, which is a problem. Now, I think I created an example like a while back, which I think demonstrates. Let me see if I can pull it up. Where did I do it? Is it this? No. Where is it? No, I've lost it. Anyways, I had this example which I whipped up in Excel which shows a cursor dimensionality, but it's gone. I didn't save it. That's all good. Let me just do this. Sorry. Anyways, so there's 2 problems. One, if the number of features is small, bias is going to be high. It's going to be perhaps too simple a model. But then as you increase the number of features, because you're sort of like you're very simply just cutting it into like just very granular specific combinations. Like you look at all the people that are, you know, female, class 3, age 45, whatever, right? It gets really granular, and each bucket will only have a small number of passengers. The problem is, as you increase features, the number of buckets increases exponentially, which means that if you have too many features, you might only have like a few data points per bucket, which is going to give you a very unstable estimate, very high variance unstable estimate, which isn't great. Let's try an alternative approach. What if we use naive Bayes? Oh, that's a fantastic idea. Let's go ahead and do that. I'm not going to go through the maths again because I think we've gone through it in some detail in these slides. So let's go through the Python code as to what is happening. Now, this is just a helper function. Basically, it just takes in an array, right? Let's say it takes an array of, I don't know, say it could look like male, female, male, right? And there's an input. Let's say, you know, your argument array, you chuck in this guy, and what we'll do is it will return a dictionary that looks like this. 1, 2, 4. It gives you a mapping of all the unique levels as well as the number. So this is what it does. Okay. Now here we are building. This is a naive Bayes object, right? And you're effectively using that formula, right? And you're sort of just building it up bit by bit. Now you may recall from your naive Bayes formula that you needed the class prior, right? The prior probability is yourself surviving or not surviving, right? And that's what this self.py is, the prior probability of survival, right? This is this guy here, this one here, probability of y is equal to y being equal to 1. And it's simply just, the prior estimate here is just the number of people that have survived, right? And again, remember that survival is coded as 1. And so all you got to do is just, you just take the number of people that survived divided by the total. That's your prior estimate for survival prior to seeing any data or features. Now, the next thing we need to do is we need to like subset up the features. So subset up the design matrix into those who survived and those who died. So basically, you cut up the design matrix. You cut up your input data set into those who survived and those who didn't survive. That way you can look at like frequencies, empirical frequencies of, given they died or given they survived. So you use this to get, given they survived. Use this to use, say, given they died. What the probability of seeing certain features are. And this is it. So then, we need, remember from our naive Bayes, we need this, right? So we've got our class prior here. Now we need the probability of x given y. That's this. So this is a probability of x given y, but there's two x's here. We have two features that we care for. We have the class and the gender. So here, this is gender. So this is a probability of gender given you survived. This is a probability of gender, the distribution of gender given you died. And you do the same thing for the class. So this basically saves to your object all these probabilities here, right? The probability of seeing the feature given the class. Now when you predict, you just apply the formula, right? You take the probability of survival is your class prior, so your survival prior multiplied by the probability of whatever gender it may be, whatever gender it is, of seeing that gender given you survived times that class given you survived. Death is the opposite. Now, this is just playing around with like odds ratios and stuff, right? But effectively, all you need to return is the probability. You want to return this guy, and it's just scaled, by what's at the bottom? You scale it by the probability of seeing all the x's, right? And that's what this will return here. Okay, so now we test out and run our model, and we can actually compare and contrast. So here's our simple model here. Just gonna copy it over. This is our, fancier naive Bayes model. It's not too far off. I mean, this is a simple example. It's a little bit different. Whether one's better or worse, you probably want to use a test data set to work it out. But, So there's a contrast in those two. Okay. So again, like naive Bayes makes some assumptions here. That they're independent, that the probability of you being in, say, class 3, working class, is independent of gender, which we know that's not true because you're more likely to be male if you're on working class. Just Titanic data set. This is how it was back then. Okay, so it's not quite the same, but it's pretty good. It's probably good enough. Again, just have a look at the test performance to see and compare and contrast the two. Now, there's a number of parameters to be learnt, scale with a number of, So the good thing about naive Bayes is it's like linear. The number of parameters you need to learn goes up linearly with the number of features for Bayes, which can make it very efficient. Why is this? Look at the formula, right? All you really care for is every time you add a feature, you just got to multiply in one more probability. It's linear. Linear, and we should all know linear is great. It is fast in general. It's linear. Fantastic. When you add a new feature, because you it's so I'd say because of the naive Bayes assumption. Ooh. It's linear. Fantastic. Cool. Now, this is naive Bayes from scratch. Now, your scikit-learn has naive Bayes. The only problem with with scikit-learn in general is that with categorical variables, it doesn't really do levels. You need sorry. Let me rephrase. So scikit-learn expects all the design matrices, all the data to be numeric. It cannot handle like male, female, like class 1, 2, well, that can't class 1, 2, 3 necessarily, but in order to use scikit-learn, you need to do an extra step. You need to deal with your categorical variables. You need to either say do your one hot encoding, which is good when like there's not really any clear relationship or rank relationship between any of the levels. So for example, male, female. One hot encoding basically just I'll get up a diagram. This is probably the most common way to go about doing it. Here we go. Yeah. So let's say you have a categorical variable like this. One hot encoding creates a new column for every level and just like encodes at 1, 0, right? Now in contrast, you might have something like ordinal encoding, which only really makes sense if there's like a rank between them. Like for example here, this makes sense. So let's say you got a temperature scale here. Actually, yeah. So let's say I have a temperature scale. It could make sense to like rank them, right? So hot's number 1 and then cold's wait. Why is it encoded like this? So 0 is hot, 1 is cold, 2 is very hot. Oh yeah, so I remember here. Yeah. So it might make some sense that encoded like this. So like it's increasing order of temperature. So cold is 1, and then warm is 2, then like hot is 3, and then very hot's 4. But you gotta be careful, right? Because if you do ordinal encoding on like gender, like scikit-learn's gonna assume there's some like rank or numeric relationship between the two, which might not be correct, which probably isn't correct. So just putting it out there, with scikit-learn, with the categorical variables, you need to do a bit of pre-processing to deal with your categorical variables. So that's what it's doing here. One hot encoding here. Okay. So you use your one hot encoder from scikit-learn pre-processing. You instantiate a multinomial naive Bayes model. You fit it, and you run your predictions. And let's compare and contrast. Yeah, it's pretty similar, isn't it? Cool. What else? Naive Bayes can also handle continuous features. Yeah, so I think I touched on it briefly here, but with naive Bayes, when we use empirical probability, like let's say that play tennis example, you look at like say the chance of it being sunny, so it's 2 out of 9. So say 2 out of 9, 2 out of 9. But if it's continuous, like a temperature like 100.12, 150.25, it doesn't really make sense, and you might have everything just like 1 on like 20, or the total number of the number of rows. If like there's no overlap, like you might have 100.11.12. But yeah, the problem being that it's continuous, and you apply like a discrete sort of empirical frequency to a continuous variable, which doesn't really make sense. So workaround. You can assume a Gaussian. You can assume normality between the two, right? So here we generate two data sets. a Gaussian mixture model. Here is one Gaussian and here's another Gaussian, right? They're two Gaussians, and we say this Gaussian is a red class, this Gaussian is a blue class, right? We plot it up here, and then we fit a, what do we use? A Gaussian naive Bayes to fit a model to create a decision boundary like so, and it's not too bad, isn't it? I mean, you look at the data, there's only a little bit of misclassification, looks pretty good overall. So I'm running low on time, aren't I? Now, the other thing we try is logistic regression. The other thing we try is logistic regression. Again, so what it is if you fit a line of best fit and you feed it into that theta there is a sigmoid squishification function. You squish that real valued function between 0 and 1, and fantastic, now it's a probability. Beautiful. Now, we use sklearn's logistic regression module. Now, bear in mind, sorry. Bear in mind that this guy here, did this not run? MX is not defined. Did I not run this? Run. Oh, jeez. Is this the wrong one? Sorry. This one. I had the wrong one open. Yeah. Sorry. So bear in mind, logistic regression. This has a bunch of parameters, and by default, it actually does have some level of regularization. So by default in scikit-learn, you are using ridge regression with an element of regularization. So bear in mind, this is like an inverse of regularization. So the higher this is, the less regularization. Keep that in mind. You can change it to L1, L2. L2 is ridge regression. L1 is lasso regression. I think they might have elastic net, do they? Oh, they do elastic net, cool. You can use elastic net. Elastic net is like a blend of these two, which is pretty sick. All right, now this is pretty heavy. You fit it here. This one actually has pretty heavy, whatchamacalls it? No, it's got very little regularization because it's high, it's inverse. Okay. And what it's saying here is you instantiate it, then you fit your model to your mixture model design matrix, your mixture model target. And here's your line of best fit. Now the thing you can play around with here, the thing you play around with here is you can play around with, what do I play around with it? No, it's standard, is it? Yeah, okay, cool. You fit your model, so this time use logistic regression. Notice how it's like a straight line. The decision boundary is a straight line, but this was a curve. Now, of course, this is linear, but remember, linear regression means linear in its coefficients, not necessarily a straight line. Now, this one here, actually, you fit like a polynomial term as well. So, in this example here, basically you're just fitting y is equal to x is equal to, say, beta 0 plus beta 1 times x1. Okay. Down here, you're fitting a whole bunch of, oh, sorry, there's a x2 as well, isn't there? Yeah. So here, not only are you fitting this, you're also fitting all those combinations. So you have this guy here, you have this guy here, and you have this guy here. I guess you could have epsilon, but whatever. This is the line you're fitting. So you're extending this by not only fitting just like the linear part, you're also fitting like all those higher order terms, all your polynomial terms like x1 squared, x2 squared. This will reduce the bias and increase the variance, potentially allowing you to model something more sophisticated. Cool, so you fit that, And cool, you can now you got this guy here. You got a curve. One thing you can do is you can play around with it. So you can try L1, L2. So interesting thing about lasso regression is, so these are all the coefficients. So this could be, intercept x1, x2, x1 squared, x2 squared, x1, x2. We could increase the regularization by doing something like that. And oops, that didn't run to it. We increase the regularization, and look, we regularize it so much you fit nothing. Look, there's no coefficients. Let's reduce the regularization. It's too big. Here we go. Now we regularize it enough so we got rid of these ones. Remember, regularization in lasso introduces a penalty. So if you increase the regularization, you might lose some coefficients. So here, those higher order terms won't fit. x1 squared, x2 squared, x1, x2, not fit. Hence this linear relationship here. Now, if we decrease it a bit more, we have, oh cool, we've got another term. There's less regularization. Let's just get rid of the regularization. Oops, sorry. Let's just get rid of the regularization, a lot of it at least. And let's just let the data just fit to it without any regularization or close to none. How do I get rid of it all? Yeah, there we go. So now everything's fit, and you can probably see it hugs the data more as you decrease the regularization. You can do the same thing with your Titanic. Yeah, cool. Sorry, so it's going on for almost 2 hours, so I'll probably wrap up here. I will see you guys during the consult during the week. Hope you guys enjoyed today's tutorial. Have a good one. Bye bye.